All right, let's get started. We are going to go through the Chapter 2 presentation today, so you should have your notes out to help you through this presentation. There is a lot, so I need to go quick, and I need to start now. Just a quick note before I do start that presentation, I did grade your problem sets from Friday. Grades are in Aspen. Those will not be handed back for you to keep. But at some point when I have extra time at the end of a class, I'll hand them back for you to look at and see what mistakes you made if you did not get a perfect score. The other thing that was posted yesterday, late morning, I posted a sample lab report for Lab 1. You should see that post under Lab Resources, so you can see what a lab report should look like when you're writing a lab and how the formatting and just the language of things. Making sure that you're trying to do things as professionally as possible. Of course, I've got 27 years of teaching experience. I've got a master's degree in engineering. I've published work when I was in industry. So my report, I was trying to mimic being a student. But it is very hard for me to get into a high school student's mind because I am not a high school student. So keep in mind that is the standard I've set is very high, but it doesn't mean you have to hit that standard. You got to be pretty close to it, though. Okay, there should not be grammatical errors. There should not be spelling or punctuation errors. This is a college class. You should be way beyond spelling, punctuation, grammar errors. And it should sound nice and cohesive. It should be, if you're having issues with that, I would suggest you speak to an English teacher, because that is their discipline, is to help you write things, including scientific works and articles. So that's where we have to get. If you're having issues with the science, that's where I help you, okay? And I am not reviewing your next lab ahead. It is, you're turning it in. You've gotten feedback from me on the first lab. I have not graded your first lab yet, but take a look at the sample. It should help you go through what you need to be doing and how to set it up and so forth, okay? Questions? Tomorrow, the assignment that's due is homework number 3. It is end of chapter problems. So please make sure that's done. They are posted in Google Classroom and in Aspen, so you can see what those are. All the Chapter 2 assignments are there. All right, let's get going. We're going to talk in this unit about motion in one dimension. So it's 1D, one-dimensional kinematics is what we're looking at. One-dimensional kinematics. So just remember what kinematics is. It's a study of motion. 400 years ago, the first measurements that help us understand motion were made by a gentleman named Galileo Galilei. And in all of our discussions of motion, we're talking about particles that are moving, not an object. So what is a particle? It's an object whose position can be described as a single point. And basically, you would consider anything at this point to be a particle so long as you can ignore its internal structure. So there should be no variations in the internal structure, and it should not be rotating. So basically, what we're talking about, things that are rigid and non-rotating. That would be a particle. So am I a particle? No. The makeup of my head is different than the makeup of my feet. Okay, so that has a variation in internal structure. And right now I'm spinning, I'm rotating, so that's not a particle either. Okay, so we're basically think of like a box, a solid box. That would be a particle. Okay. The first terms you have to be familiar with are those of displacement, velocity, and speed. We use different variable letters. When you read the text, you should have noticed that. When you look at your AP reference table, you should notice that. We do not use a D. We do not use VI. We do not use VF. The only letter that will be the same is A and T. That's it. So we're going to start with position along the x-axis. We write it as an X. So basically, it's like an X coordinate. This tells you where you're located on the x-axis. Has dimensions of length, which are meters usually. In your textbook, they do use XI and XF, but on your AP reference table, it's X0 and X. X0 means your position on the x-axis at time 0. Your position at time 0. That's read as X0. Or sometimes you'll hear people refer to it, if you're at a college lecture, they would call that X0. x naught. We're going to call it x0. I think that's a little easier. So if I'm looking at a position at 1 second, what I would do is write x1. If I want a position at 5 seconds, what would I write? x5. Now, x by itself just refers to a final position at some arbitrary time. Okay, there's no specific time. It's just some ending time. A displacement, therefore, is a delta x, the net change in position with dimensions of meters. So you'll take your final and subtract your initial position. So on this diagram, we're going to take this coordinate, subtract this coordinate, and that gives us our displacement, delta x. Velocity is v, the rate at which your position is changing with dimensions of length over time, so meters per second in the metric system. Instead of writing v bar, we can write VAV. You can stick with the bar. I don't even think that's on your reference table. How to get an average velocity, the ratio of your displacement to your time. It is not a distance divided by time. It's a displacement over time. V bar would be the delta x over t. Your position, your displacement, your velocity, your average velocity things are all vector measurements. As you know, they all have to have a direction. In one dimension, we can use a sign. Next chapter, we get to two-dimensional motion. You can't use a sign anymore. So in one dimension, you can have a sign, but you have to indicate what that sign is. Plus doesn't always mean to the right. It could mean left, if you define left as the positive direction. Position, positive is usually to the right of the origin, negative to the left of the origin. So if you had a positive velocity, displacement, or average velocity, that would indicate motion in the positive x direction. Negative would be negative x direction. Okay, let's now talk about average speed. Average speed is different than an average velocity because you take a total distance traveled and you divide by time. In your textbook, they use total distance is the letter S. We use the same letter V for an average speed as we do an average velocity. So the only way you would know the difference, we're going to use some additional notation, which you should have seen in the text to indicate how we write them a little differently. So average speed is not the same thing as an average velocity. That's number one, because speed is going to be a scalar measurement. It will never have a direction on it. There's a mistake here on the slide. It says average speeds are always positive. That's incorrect. Nor are distances and times always positive. That is incorrect. If I'm saying it's positive, it means we put a plus sign out front. That plus sign is a what? It's a direction. Does a distance have a direction? No. Does a time have a direction? No. Therefore, speed can't have a direction. It should not have a plus sign out front of it either. It is unsigned. Unsigned is the better term to use. They are unsigned quantities. Your average speed is also not the same thing as the magnitude of your average velocity, and that's because the distance traveled can be much different than your displacement. So on this picture from the textbook, if I moved from the 0 meter position to the 100 meter position in 12 seconds, and then I reversed and came back to the 50 meter position in another 30 seconds, to get the average speed, I would add 100 to 50. 150 meters divided by a total of 42 seconds. To get my average velocity, I would take the displacement, which would be 50 meters to the right, and divide by 42 seconds. It gives me a very different value. Now, let's talk about how you get velocities from position time graphs. This is stuff that you did last year. Okay, so this is all review so far. To get a velocity from a position time graph, you look at the slope of your graph. Now, if you're looking for an average velocity, you're looking at the slope of a secant line that connects the two positions on that position time graph. Remember what a secant line is? It's just a line that connects the starting and ending positions. If you are looking for an instantaneous velocity, a velocity at one moment in time, then you have to draw a tangent line at the point on the curve that you might have, and then find the slope of that tangent line. So what that means is that your instantaneous speed, sometimes we say, is the magnitude of your instantaneous velocity at a particular time. So on this graph of position versus time, x versus t, again, that's position along the x-axis, we're moving from point 1 to point 2 here in this somewhat segment of a parabola. So if I wanted to know my average velocity from point 1 to point 2, I would just draw in this blue line, that's a secant line, and find the slope of it. If, however, I want to find my instantaneous velocity at this point right here, I would then draw a tangent line to that point and find a slope at that point. You will not be doing that in this class. You just have to know conceptually that that is what you do. Finding the slopes of secants and tangents is something in calculus. You're going to be using a calculus function now to help you find those. And that way, there is no wiggle room on what the answer will be. Because if you're drawing a tangent line, you know, what's this tangent line versus this one? They have slightly different slopes. And then there's a margin of error in terms of what you're doing. We're not going to have any errors. This is why one of the reasons calculus was developed, to make sure we get exact answers. And we'll talk about that in a minute. So the instantaneous velocity is therefore the same thing as the limit of a ratio of delta x to delta t as your delta t approaches 0. And I know you talk about limits in pre-calc, right? Are you going to be asked to do a limit in this class? No. Because the last thing you talk about in pre-calc is what a limit becomes in calculus. Do you remember what it becomes? Starts with a D. A what? A derivative, that's right. So we're going to be using derivatives for that. Now, even if you didn't talk about it in pre-calc, you watched a video on this over the summer that explained all of this to you. And that is where I'm expecting you to go back. That video is still posted in this Google Classroom. The summer one's still there too. So you may want to go back and watch that video on how to do a derivative if you don't remember. So that limit is a derivative. So if we want to find an instantaneous velocity, and I know my position function, the position is a function of time, I just do the derivative of that expression. And then I evaluate it at whatever time I want to know the velocity at. Okay? So the velocity of a particle is the time derivative of its position. Now this notation looks a little funny. Let me show you how you'll probably see it. So velocity is v. When I write this, I'm talking about my velocity as a function of time. We say that that is the derivative of the position with respect to time. That is read. That statement mathematically is read as the velocity as a function of time is equal to the derivative of the position with respect to time. You're going to see that some of the equations we develop will be in terms of other variables besides time. You need to know what the variable letter is in the equation, which is what you're looking at the derivative of. Okay, so we're looking at the derivative of the position with respect to time. On your AP Physics reference table, there is a chart showing you what the derivatives of specific functions are equal to. So let's go over how these are read. You can also look at Appendix M, I believe it is, or I'm sorry, Appendix D at the back of your textbook, which will show you on pages AP 23 to AP 27 how to do these derivatives. But these equations are from your reference table, the pink sheets, which you have access to whenever you are doing a test or quiz and classwork. So the most useful rule is what we call the power rule. And let's talk about how this equation works. For now, your derivatives are going to be limited to this particular function. So let's say that my position function is some constant c times t to the nth power. To evaluate that position function's derivative, where t is the variable, how do I know that? Because it's in the denominator of this derivative function. What I do is I keep my constant out front. I take that power of n, I move it out front, and then I subtract 1 from the power. That's how that derivative is evaluated, okay? So let me show you how that's done. Let's do an example with some numbers instead of generic letters, okay? And if you understand it, great. If you don't, we'll talk about it some more. Because you do need to understand how to do this derivative function. So let's say that your position as a function of time is 3 times x to the 4th power. And my question to you is not going to be what is the derivative of that. That would be how your math teacher presents the question to you. How am I going to present that question to you? My question is going to be, what is the velocity equation? And you need to know how to get it from that position equation, right? What are you going to do? What's the mathematics? It's called a what? A derivative. You now need to do the derivative of this. So the rule says that you keep the constant, you multiply by the original power, you keep the variable, and you raise it to that power minus 1, which gives us what as our velocity expression? 12x cubed. That is the derivative of, I'm sorry, not 12x cubed. My mistake. This should be a t, because the variable is t. 12t cubed. All right, so you all have calculators. What we can now do is evaluate that to determine what our velocity is at any time. So if I want to know what is my initial velocity, we're going to call it v0. What am I going to do? I'm going to plug in 0 for the time. What does that mean my initial velocity is? 0 meters per second. If I want to know my final velocity, I need to know what time I'm talking about. Let's say I want to know my velocity at 5 seconds. What would I do? That's right. So I would have 12 times 5 cubed. So what does that give us? 1,500 meters per second. That's a lot easier than trying to draw a tangent line and finding the slope of that. Certainly a lot quicker if I know what the equation for the curve on my position time graph is. You follow what I'm saying? But you have to know, first of all, that to get your velocity, you must do the derivative of that expression. And then if I want to know it at a time, I just plug that time value into that new expression we just came up with. Make sense? Okay, any questions on how to do that derivative? That's as complicated as the derivatives are going to get right now. In a couple of months, you're going to have to do them all. Because I know by that point you will have done derivatives in your AP Calculus classes. So all types are there. So derivatives of sines, cosines, natural logs, e to the x, x to the n, and the top one is called the chain rule. So we'll be using that as well. All right, so can you tell me, if my position function is equal to 5t squared, what's the velocity equation? 10t. Yep, 10t. 5 times 2 times t to the 1 power, which is 10t. Very good. All right, now let's talk about something called relative velocity. Relative velocity is always measured, anytime you're measuring a velocity, it's always measured with respect to some reference frame. So take a look at this picture, which is from your textbook. They're showing you mid-air refueling of a jet, which they do a lot in the military. So this is a fuel plane dropping a fuel line down to this fighter jet, which cannot land. It can't, based on the military maneuver it's trying to do. In order to refuel it, they have to be moving at the same speed with respect to the ground. If they're not, is this connection going to stay there? No, okay, either this plane's going to be coming back or it's going to be moving ahead and it's going to disconnect and fuel's going to land on the ground. So that relative velocity would be the velocity of this with respect to that. In other words, we consider this velocity to be our 0. So we need that relative velocity to be 0 so that way they are moving at the same speed with respect to the Earth. Let's see, do I have the video linked? I do. There's a really cool video which explains relative velocity out on YouTube. So I want to show this video to you. It's pretty cool.
I'm going to ride on a moving train attempting one single run from start to finish.
Nobody has ever done this before. It's a world first and we don't even know if it will work. David will need to test it in the train yard before he does it moving.
It's probably gonna be hard for spins, 360s. It's pretty narrow.
What about the train moving?
Yeah, we'll see.
It's gonna get weird. We have some creative features here, like this step up into a regular box into step down. That's pretty sick. Check it out how tall it is. When he spins and the truck is moving, it's gonna make him dizzy.
Do końca, na końcu schody. Schody są ciekawe, tam jest wyżej niż myślałem, że będzie.
The last trick has never been done before on a mountain bike. It's gonna happen here on this set of stairs. Flat drop backflip. It's a world first.
Go, go, go. Myślałem, że dokręcę.
It's stressful. Hopefully he does it so we don't have to stress anymore.
No, smakujesz, ty tyle trenowałeś na tropie u nas, że...
On a moving train, this will be super hard.
Nie mam mniejszej idealnie w ostatnim schodach wylądowałem.
Now you gotta do it while it's moving. There are 3 major challenges to ride the whole train when it's moving, which nobody has ever done before. First challenge, the wind. Too much crosswind, and he will be blown off the course in the air. There is no room for mistakes.
Jak tam film, mamy takie sketchy, że rady tak, tak bez na boki się jeździ. Takie mam uczucie.
Second challenge, the speed. The train and David. They both have to go in a perfect speed in order to make everything go alright.
Everything is moving, but the course is not moving. That's a weird feeling, and I also feel in the air that I'm going back kinda, so I'm going to let it. Luckily, we will lower the speed a bit. When we actually have the speed we need, my head is tripping.
Third challenge, landing the tricks. David has chosen some very hard tricks to land.
I need to be really exact, precise.
He has to get all of this in one line, or he has to start again.
Drop.
Oh, David hazed the second jump. Not this time. This is sketchy.
Another day in the office.
David misses the front flip up just before the last trick. I have a feeling he's gonna go for it now.
Looks like he's staying in the same horizontal position, doesn't it? That's because his velocity towards the
He's
back
gonna
of the
get it
train
now.
is the same as the forward
It's gonna
velocity.
happen.
Oh my god.
Whoa. Dawaj, David. Yes, it's happening. Ah. Ow. He slipped his foot on the last tree. I będzie musiał poprawić wszystko.
Ostatni przejazd to będzie.
I was just doing one by one, waiting for the last one.
Oh, I can believe it.
Pretty
He
cool,
has
huh?
just done it.
That video was the inspiration for that ceiling tile that last year's group decided to design at the end of the year. So, all right, let's move on. Let's now talk about the term acceleration. Remember that acceleration is going to still be a lowercase a. Please do not write a capital A. Capital A means something else later in this course that we'll talk about. When we talk about an acceleration, we're looking at the instantaneous rate of your change in velocity, usually measured in lengths per time squared, so meters per second squared in the reference metric system. Very often we refer to accelerations as speeding up, slowing down, or changing direction. You will not ever use the term decelerate. It is ambiguous as to what that's referring to. We'll either say speed up, slow down, or change direction. And in this course, last year you were limited to only speeding up, only speeding down, or only changing direction in a problem. Right? Not this year. Now an object could be doing speeding up and changing direction at the same time, or slowing down and changing direction at the same time. So we'll be looking at problems like that this year as well. So when I talk about an average acceleration, we're looking at the ratio of the change in your velocity over the time. So on a velocity time graph, the instantaneous acceleration would be found by looking at the slope of a tangent to your velocity time curve. In Regents physics, every velocity time graph that we showed you was a line. That's not going to happen this year. We're going to have changes, non-uniform changes in velocity, because that's more realistic to the real world, which means that we have to understand that to go from a velocity to an acceleration, I have to look at slopes of tangents to curves. What is the slope of a tangent line? The same thing as in calculus? We just talked about it about 5 minutes ago, Jerry. In calculus, you're not going to be finding slopes. It's called a derivative. So we're going to be doing, again, you could say it's a limit, but remember a limit is the same thing as a derivative. So to get your acceleration, you're now going to be looking at derivatives of velocity equations. So, I just erased my velocity equation. I'll put it back up here. We just came up with our velocity equation a little bit ago as 12t cubed. If I want to know my acceleration equation, I got to take the derivative of what I just found. So what would my acceleration equation be? With you? 36t squared. That is correct. 36t squared using that chain rule that we just talked about, or the power rule. And then if I want to know my acceleration at any moment in time, I would plug in that particular time to come up with the acceleration value at that time. Exactly. Now this is showing you a couple different ways to write that. We're saying that our acceleration is the limit of our velocity as time approaches 0. Okay, we're never going to do that. Don't even worry about that. Here we're saying that the acceleration is the derivative of our velocity with respect to time. Or, now let's talk about what this notation is. You'll see this when you get to the AP Calculus course. It is also the second derivative of your position with respect to time. Because think about how we got that acceleration. We actually did it in 2 steps. I started off with a position equation, didn't I? And what was that position equation? Wasn't it 4? Nope. 4 times t to the, was not 4. Was it 3? 3 times t to the 4th power. I'm trying to remember what I had written. 3 times t to the 4th power. So a second derivative just means you're going to take a derivative and then do it again. You're doing 2 derivatives in a row. That's what a second derivative is. But that is how you write it, d to the 2nd power x with respect to t. These D's refer to derivatives. Okay. I gave you a calculus, all the calculus you need for this course in 4 pages, 2 pages stapled together. It was one of the initial handouts I gave you on the first day of school. You may want to look back at that as well. It will give you, here's the notation, here's how we write it, this is how it's read, here's how you do some things. So remember that if your acceleration is 0, that means your velocity is not changing over time. So your velocity is constant. So your velocity time graph has to be a horizontal line, and your position time graph would be a diagonal line. Then if your acceleration is not 0, but it's constant, which is, these are all the cases we talked about in your Regents physics course, then your velocity time graph would be a diagonal line and your position time graph would be a parabola. We are going to see in this course that we have non-zero, non-constant accelerations as well. And if that is the case, your velocity time graph is some type of curve. I can't say it's always a parabola. It could be cubic, it could be a 5th order curve, it could be anything. Okay? Anytime your velocity time graph is a curve, your acceleration is not uniform. It is not a constant value over time. The methods you learned last year in Regents physics and all of those kinematics equations we had last year, they still work, but they only work in very specific cases, those right there, where the acceleration is a constant value, either 0 or some other number. That acceleration doesn't change. As soon as the acceleration is different over time, you have an acceleration of 10 meters per second squared at 0 seconds, but an acceleration of 5 meters per second squared at 1 second. That's not a uniform acceleration. You cannot use any of those kinematics equations that we learned last year. You cannot. And if you try to, the whole thing is wrong. You have wrong physics. The way you solve those is all through calculus, all derivatives, and the opposite of a derivative, which we'll get to in a minute. Let's go back to what we talked about last year, constant acceleration. If your acceleration is constant, your average and instantaneous accelerations are the same. So your velocity could increase linearly with time if you have a positive acceleration. Your initial velocity is going to be v0. Remember the velocity at time 0. Your final velocity at some arbitrary time is just v. So these were the equations we saw last year in Regents physics, but they're written with the AP physics variable letters. So this first one is VF is VI plus AT. That's how you saw it last year. This next one is V bar is VI plus VF over 2, the average of 2 values when your acceleration is constant. This one is D is VIT plus 1/2 AT squared. And this final one is VF squared is VI squared plus 2AD. You have to get familiar with using the AP symbols. Where are you going to find those? On your reference table, the pink one. You want to start getting familiar with that. Maybe check those equations off now so you know where they are and that those are the ones you can use. Okay. Do you see them in the mechanics page here? Do you see those kinematics equations? They should be the first 1, 2, 3. The first 3 on the left-hand column of page 2 of your pink reference table. That's it. All right, let's talk about if you're in free fall. That's when you're falling under the sole influence of gravity, no air resistance. If you are falling in free fall and you have 2 objects that are both dropped, they're going to have the same initial velocity and they move together. Their mass doesn't matter. Their mass does not matter. We know that from the Regents course. When we talk about accelerations due to gravity, in this course, look at page 1 of your reference table. You should see that the acceleration of gravity, is it listed there? Yep, second one in the constants list is 9.8, not 9.81. Please do not use 9.81. That would be marked wrong. It is 9.8 in the AP college course, okay? Your textbook answers are all worked out with 9.81. So when you get an answer, please work it out with 9.8 and just recognize it's going to be really close to what's in the back of the book. Maybe it's off by a tenth or a hundredth. It's going to be off by just a little bit. G, when we use the lowercase g, that's just representing the magnitude of that acceleration of gravity. So if you define down to be the positive direction, then your acceleration of gravity would also be positive. If you said up is positive, then your acceleration of gravity is negative. Now, in this scenario with skydiving, this is not free fall. Why not? Why is skydiving not free fall? Yeah, there's a lot of air resistance. In this course, we're going to do a lab, and we have to understand how to solve problems with air resistance. That gets to chapter 5, when we get to chapter 5 of the text. But I just want to show you some kind of fun stuff you can do when you have air resistance. Down in Westchester County, if you head down the thruway, there is a place called iFly that you can go to where you get to actually practice getting into a flight suit with air resistance, doing some pretty cool
up to
stunts.
150 miles per hour, allowing users to experience a condition much like that of free fall. Divers wear a baggy flight suit which provides a large surface area. The upward force supplied by the current of air is balanced by the downward force of gravity. Experienced divers make continual adjustments to their body shapes to maintain this condition of balanced forces and therefore sustain lift. During the adrenal rush of an authentic skydive, the divers begin to accelerate downward due to the force of gravity while experiencing a drag force produced by the air around them. As the diver's speed increases, so too does the drag force, eventually becoming equal to the gravitational force. At this point, the diver is moving with a constant terminal velocity. Divers are able to perform elaborate acrobatic tricks by altering their body shapes. This alters the amount of surface area and in turn affects the drag force. Of course, to witness the most dramatic example of surface area affecting drag force, you need only pull the ripcord.
All right, so that would be a pretty cool field trip, but it's way too expensive. It's like $200 for an hour at that iFly. So it's not something that I think you all just have hanging around. $200 to go have fun for an hour. So we're not going to do it. But if you end up, maybe that's a graduation gift you want to ask for. Hey, Mom and Dad, I want to go to iFly and practice what I learned in AP Physics. Okay. The last section of the chapter is about something called integration. Integration is the opposite of a derivative. Sometimes we call it an antiderivative. So if we're going in this direction, to go from position to velocity to acceleration, we do a derivative. If we're going to go in the opposite direction, we do an integral. That's what it's called, an integral. Doing an integral is called integration. So what is integration? It's the opposite of differentiating or taking a derivative. Finding an antiderivative of a function is related to what we learned in Regents physics, finding the area under a graph, between the graph and the time axis. So if you're looking at any time last year where we asked you to compute an area, or we taught you to compute an area, that is now in calculus something called an integral. Now, how do you do an integral? Again, AP, the appendix D, pages 27 and 28 at the end of your textbook will show you. You also have your calculus handout and the video that I shared with you this summer, which will show you how to do it. Your reference table also has the integral functions. The notation looks really funky. This symbol out front is called an integral symbol. It's a very long elongated S. Looks like that. That's the integral symbol. And that's the integral symbol. After it, we give you the function. We're telling you after it what variable you have to take the integral with respect to. So if I wanted the integral of x to the nth power, it's showing you how to get it right here. You're going to do 1 over that power plus 1 times x to the n plus 1 power. That's how you determine what the integral is. Right now, that is the only integral that I expect you to be able to do. The other ones will come once you've learned integrals in the AP Calculus course, which is second half of the school year. And I think that's it. Yep, that's the whole presentation. Okay? I'll see you tomorrow with homework number 3.